Hello, this is Dr. Hanaa Assil, and this is IGCSE Edexcel Chemistry, and we're talking about energetics. That means we're talking about exothermic and endothermic reactions. So you should realize that an exothermic reaction is a reaction that gives out heat. Now, what does that mean? That means if I have a reaction in that flask, the reaction inside the solution is giving out heat. Now it's giving out heat to what? It is giving out heat to the surrounding solution in the flask, and that means the temperature of the solution rises or increases and the reaction becomes hot. An example of exothermic reaction is any burning of any fuel or combustion of any fuel. All combustion reactions are exothermic. Now, on the other side, there is endothermic reactions. Endothermic reaction is a reaction that takes in heat. Now, that means if I have a reaction going on in that flask, the reactants inside the solution are taking in heat. They are taking in heat from what? They're taking in heat from the surrounding solution in it. So the temperature of the solution will decrease or go down, and the reaction will become colder. So if he says that a reaction, the temperature went up, then it is exothermic. A reaction when temperature went down or decreased, it is endothermic. In most cases, changing from solid to liquid to gas, in order to change a solid to liquid, I need to give it heat. In order to change a liquid to a gas, I need to give it heat. So these are endothermic reactions. You will be required to draw something like this. This is called a reaction profile diagram. Now, a profile diagram will show the delta H and the activation energy. What do these mean? We know that the reactants will have a certain amount of energy. Now, which reaction is this? This is an exothermic. That means the reactants will give out heat. That means the products will have less energy than the reactants. So first of all, products have lower energy than reactants. That is an exothermic reaction. Now, the delta H, can you see that triangle with an H? This is called the delta H. This is the representation of what we call enthalpy change or heat change. So if he says, what does this triangle with an H mean? We call it delta H, but what does it mean? It means enthalpy change or heat change. Now, for an exothermic reaction, we know that the products have less energy than the reactants, and that means the difference in energy or the heat change or the enthalpy change would be a negative number. So if delta H is negative, this is an exothermic reaction. Now, to go from reactants to products, we have to go through something called an activation energy. The activation energy is the minimum amount of energy needed to start a reaction. So if I have reactants, I need to give them some amount of energy, a little push in order to react. Now, this activation energy is the distance or the difference in energy between the reactants and the top of that hill that we have. That is the difference in energy between the reactants and what we call the intermediates in the reaction. So activation energy is from the top, from the reactants to the top. Delta H is the difference in energy between reactants and products. This is a reaction profile diagram. But if he says draw an energy level diagram, you do not need to include activation energy. You just need to show where are the reactants and where are the products, and that the delta H is the difference in energy between reactants and products. Now notice that in this graph I wrote reactants and products, but actually if we're talking about a specific reaction, then I should specify what my reactants are. So instead of writing the word reactants, I will write something like C plus O2 or whatever, and the product, whatever the product is, CO2 plus H2O, whatever, then you actually write what the reactants are and the products are. for an endothermic reaction. Remember we said endothermic reaction means the reactants gain energy or they take in heat. Now, when they take in heat, that means that the products have higher energy than the reactants. And the delta H is the heat change or the energy change or the enthalpy change. It is the difference in energy between the reactants and the products. Now, since the products have higher energy than the reactants, then in endothermic reactions, the delta H is a positive number. Again, the activation energy is the difference in energy between the reactants and the intermediates or the top of that hill in the diagram. This is an energy profile diagram. Again, if I'm required to draw an energy level diagram, I just show the energy of reactants and the products and the delta H. The delta H in this case, in an endothermic reaction, the delta H is positive. To calculate delta H, we have two methods in this syllabus. Either we use bond energy or we're going to talk about a different method. Now, what is bond energy? Bond energy is the energy needed to break a bond. And that means if I have a reaction, for example, hydrogen plus chlorine to give 2HCl, what is happening in this reaction? The bonds in the reactants are being broken. And in order to break the bonds in the reactants, we have to give it heat. So it's going to take energy to break the HH bond. And we're going to add energy to the reaction in order to break the Cl-Cl bond. Now, when the two HCl bonds are formed, they release energy. Now, how much energy? That is what we call the bond energy. So you should realize that the bond breaking in reactants is an endothermic process. You add energy in order to break bonds in reactants. Now, the formation of bonds in the products is an exothermic process because when the HCl bonds are formed, for example, that gives out heat and that is an exothermic reaction. Now, overall, is this reaction exothermic or endothermic? Well, that depends. Do I need to add more energy than is released? Or is it releasing more energy than it needs? So the overall delta H is the energies I need to add in order to break the bonds in the reactants minus the amount of energy released when the bonds in the products are formed. If overall the delta H here is positive, then the overall reaction is endothermic. That means it took in more than it gave out. If the delta H here is negative, that means the reaction overall is exothermic. That means it gave out more than it took in. Do we understand this? So for this reaction, for example, you are provided with the bond energy, so you don't need to memorize any of these numbers. So he will tell you that to break the HH bond, I need, for example, 436 kilojoules. To break a Cl-Cl bond, I need 242. And the HCl bond, the bond energy is 431. Now, in order to calculate the overall delta H, to break the HH bond, I need to add 436. I need to give the reaction 436, so that's a positive number. To break the Cl-Cl bond, I need to give it 242, so that's a positive. Now, when the two HCl bonds are formed in the product, they release energy. They give out energy. That's a minus. That's a negative number. We have two HCl, so multiply the 431 by 2. Now, overall, is this reaction X or endo? Well, reactants minus products. In this case, it gives you an overall negative number. That means that this reaction is exothermic, since when we say a negative number, heat is lost to the environment. Again, another example. Here he's saying hydrogen plus oxygen to give water. And he shows you the bonds. And he gives you the bond energies. And he's saying calculate delta H. Again, reactants minus products. So what do we have in the reactants? The energy taken in to break the bonds in the reactants, I have two HH bonds, each of them is 436. I have one O double bond O. Remember that we're talking about the bond as a whole. So to break the double bond between two oxygens, I need 498. I have only one of them. I have one bond, one double bond between the O2. Now, in the water, we have how many bonds of OH? He's telling me each OH is 464. But how many OH bonds do we have? Now, each water molecule has two OH bonds. We're looking at the bonds. So one OH on this side, one OH on the other side. But I have two water molecules. That means I have a total of 4 OH bonds. Now, reactants minus products, that gives me delta H, and the delta H overall comes out as a negative number. Here he's saying complete the energy level diagram. Of course, if I have the delta H as a negative number, that means it is an exothermic reaction. That means my products have lower energy than the reactants, and the delta H is the difference in energy between them. Notice that when I wrote this, I wrote the actual reactants. My reactants are 2H2 plus O2, and my products are 2H2O, and I show where delta H is. Another example, here we have nitrogen plus 3 hydrogens to give 2 ammonia. Now, what are the bonds that we have? I have a triple bond between the nitrogens. Now, he's telling me that to break this triple bond between the nitrogens, I need 941 kilojoules. To break each HH bond, I need 436. To form each NH bond, it will give out 391. Let us take a look at each of them. So, I have one triple bond between two nitrogens, and that is 941. We don't multiply the 941 by 3. He is telling me to break those 3 triple bonds between the nitrogens, I need 941. I have only one of them. Plus, the HH bond is 436, but I have 3 hydrogens, so I have 3 HH bonds. So I multiply that by 3. And these are for the reactants, so these are positive numbers. Now, minus the product. What do I have in the product? He's telling me that each NH bond needs 391 or gives out 391. Now, how many NH bonds do we have? For each ammonia, I have 3 NH bonds, and I have 2 ammonia. And that means I have a total of 6 NH bonds. Overall, my delta H is a negative number, so we say that the reaction is exothermic since heat is lost to the environment. Again, another example. Let us look at the bonds, and he gives me the bond energies for each bond. So what do I have? The energy needed to break the bonds in the reactants. Well, what do I have? I have CH bonds. I have 3 of them. The CO bond, I have 1, and that's 360. Then I have an OH bond, that is 463. And then I have O double bond O, I have 1.5 of them. So the 496 I multiply by 1.5. All of this will give me the energy needed to break the bonds in the reactant. So that's a positive number. Now, in the products, the energy given out would be, I have the C double bond O. How many C double bond O's do I have? I have a 1 C double bond on one side and 1 C double bond on the other side. So in the carbon dioxide, I have 2 CO bonds. And then the OH, again, I have 2 water. Each water has 2 OH bonds, so I have 4 OH bonds. Overall, my reaction is exo because the delta H is a negative number. So that is one way of calculating the delta H. But in another method, you can calculate the delta H when he says that he did a reaction. And usually the reaction is made in something called a calorimeter. And we measure the initial temperature and the final temperature. Remember that we use a calorimeter, which is basically a polystyrene cup or a plastic cup, in order to prevent loss of heat or to minimize loss of heat to the environment. Okay, then he will give me a reaction and he will say that it started with a certain temperature, it ended with a certain temperature. Now calculate delta H. In order to calculate delta H, we need to know these two equations. The first equation is Q is equal to mc delta T. Here the Q is the quantity of energy that we have for this reaction. Now what is M? M is the mass of a solution. Remember that any solution is mostly water, and the density of water is 1. Density is mass over volume. So if the density of water is 1, that means that the mass of water or the mass of a solution is the same as its volume. So if he says he used 25, for example, centimeter cubed of a solution, the mass is 25 grams. So remember that we're dealing first with mass of a solution. What is the mass of the solution? Is the same as the volume. Now, C is the specific heat capacity, and just know that for our purposes, C is basically 4.18. So wherever you see C, just put 4.18. Now, delta T is the temperature change, the difference between the two temperatures. Once we get Q, now I need to get delta H. Delta H is the quantity of energy per mole. So I have to divide the Q by the number of moles. Do you remember how to calculate number of moles? We said we calculate number of moles based on what he gives me. So if he's given me a mass in grams, the number of moles is mass over molecular mass. If he's given me solutions with concentrations and volumes, then the number of moles is concentration times volume. Okay, let's take a look at this example. So he's saying find the enthalpy change, that's delta H again. For this reaction, he added magnesium to 100 centimeter cubed of 2 mole per decimeter cubed copper sulfate. The temperature rises from 20 to 65. Now we're trying to get delta H. That means we need to start by calculating Q. We said Q is mc delta T. What is M? M is the mass of the solution. He's using 100 centimeter cubed of solution. That means he has 100 grams. C is 4.18. Delta T is the difference in temperature. The result that comes out from this equation is in joules. So the quantity of energy that you have out of this equation is in joules. This is usually a big number, so we usually divide it by 1,000 and change it to kilojoules. So now we have the Q. Then I need to get delta H, and we said delta H is Q over N. Okay, what is N? Now let's take a look. What did he give me? He gave us volume of copper sulfate. He gave me the concentration of copper sulfate. That means I'm going to calculate the number of moles by the equation that says concentration times volume. 2 times, remember the volume that goes into this equation. If he gives it to you in centimeter cubed, you have to divide by 1,000 because it has to be in decimeter cubed. So this comes out to be 0.2 moles. That means that my delta H would be the Q that I got divided by the number of moles. But I'm going to remind you that delta H must have a sign. So we're dividing 18.81 by 0.2. I got 94. Now, why am I writing a minus? Why did I say that delta H is a minus? Well, let's look at the reaction. What happened in the reaction? He said the temperature rises from 20 to 65. Now, when the temperature rises, that means it's an exothermic reaction. And we said exothermic reactions, the delta H must be negative. Okay, this is another example. He says the student burns 0.75 grams of heptanol in a burner, as you see. He calculates Q to be 19 kilojoules. So he has already calculated Q. And he said Q is 19 kilojoules. Now use this information to calculate the molar enthalpy change. Remember, molar enthalpy change is delta H for the combustion of heptanol. Okay, so he gives me Q and he says I have 0.75 grams of heptanol. That means I need to calculate number of moles first. Number of moles in this case would be mass over molecular mass. So I get the number of moles. Then the delta H would be the Q that he gives me over the number of moles. Again, I must put a sign. Now here, should I put plus that number or minus that number? What is he doing? He's doing combustion. Combustion of heptanol. When you burn anything, it gives out heat. And that means that it's an exothermic reaction. That means this number must have a sign of minus. It's a negative number. This is another example where he says he did titration. He did potassium hydroxide. He put 25 centimeter cubed of potassium hydroxide. The starting temperature was this. And then he added acid, 25 centimeter cubed of acid, and he got a higher temperature, 35 degrees Celsius. Calculate Q. Okay, what is M in this case? We said M is mass of solution. What is the mass of solution here? Can you see that he put 25 of potassium hydroxide and 25 of acid? So his mass, total mass is 50 grams. The difference in temperature we get, and the Q would be the M, which is 50, times 4.18, which we said is C, times the difference in temperature. This gives you a certain number. Again, remember that the number that comes out for Q is in joules. Q does not have a sign, so don't put plus or minus for Q. It is only delta H that should have a sign. This is another reaction where he's saying a student uses this apparatus to find the increase in temperature of water when methanol is burned. And he has mass of burner and methanol before combustion, then mass of burner and methanol after combustion. And he has the mass of the water in the beaker, the temperature of the water at the start and the temperature of the water at the end. First, he's asking for Q. We said Q is mc delta T. What is M? Which mass am I going to use? M is the mass of the water, and the mass of the water is 125. So we get a Q in joules. Then he says the relative molecular mass of methanol is 32. Try to get delta H. Now, how do we get delta H? We need which equation? Mass over molecular mass or concentration times volume? Of course, we don't have any concentration here. So we're talking about mass over molecular mass. Of what? Of methanol, because he wants delta H for combustion of methanol. What is the mass of methanol used? Well, if you look at the table, he says mass of burner and methanol before burning and mass of burner and methanol after burning. So the difference between that will give you the amount of methanol that was actually burnt. Now, from that mass, I can get the number of moles, mass over the molecular mass, and he already gives me the molecular mass. And that means that I can get delta H. Delta H will be the Q that we calculated up there. It was in joules. We divided by 1,000. That's why now it's 18.9 over the number of moles that we got. And we have a value for delta H. I have to put a sign. Again, the temperature of the water went up from 22 to 58. This is a combustion reaction. So this is an exothermic reaction. The delta H has to be negative. Okay, thank you for listening. I hope you understand this better. And in the next video, we'll be talking about questions and answers on this chapter. Thank you.